Heyo, how's everyone doing? Blake, good to see you in the chat. Who's all here right now? We got Blake. Anyone else? It's time to do some work. It's Tuesday. We got work to do. Got a lot of fun right here. Let's put on chiller music and that. I need to reorganize. I thought about putting that over there to like a music thing. Maybe I should do that later today. Got a bunch of stuff on here. So many things. Blake, good to see you. Just you for now. That's awesome. Chapter 6 quiz? Yeah, let's do some Chapter 6 quiz. Let me get my Pearson loaded up. I got to enter in some zeros, Blake. Man. The number one thing, Blake, I got to put in incomplete work zeros. It's a bummer. I don't know why it doesn't autocomplete. Like, you would think that it would just put them in if people didn't do it, but there's no option on it. So sometimes instructors have waited to like the whole semester to input zeros. Woo! You don't want to do that. You have to manage incompletes. I'm doing it right now, and I think I'm like 1 or 2 assignments behind. So, just 2. It's the homework and the quiz. We're doing pretty good. Only not a lot of people didn't do it. I'm very happy with that. So, a lot of people did the work. We like that. Yeah, awesome. Sometimes it's tough. I wonder how. Let me look at the grades real quick, and then we'll get some Chapter 6 quiz going right here. No zeros? You no zeros. Let's throw you 1,000 points for being here, Blake. Blake, I think you're one of the leaders. Blake, we got to make sure we keep throwing out some crazy points because we got to get people to 500,000 by the end of the semester to get to that max level. You're doing great there, Blake. You're one of the leaders. We love that. So keep it up. Let me look at the assignments right here, and let me look at the quizzes. Chapter 5 quiz. Grades were not that bad. I don't know. Actually, I think it's one of the better grades we've had on it. I can say the average. The average was a 78.4, and the median was an 87.5. So overall, not that bad, but sometimes people just stop doing the work, and that's what I see is, unfortunately, some people just stop, and there's less hundreds. So trying to get those hundreds is key, and the more hundreds you get, the better you do. Hey, Amanda, good to see you. Mubot is here, dropping those points. What was the standard? Ooh, good question. I'd have to download the data. They don't report that. I would say standard deviation is probably about 10, and it's probably not normally distributed. It's probably what's skewed. What way do you think grades are skewed, Blake? Let's throw 1,000 points for Amanda being here and Blake asking those top tier questions. Amanda, if you have any questions, let me know. Mubot is doing well. So Mubot is doing great. Oh, yeah, left skewed. Hopefully left skewed. Yeah, if it were to be right skewed. Lindsay, good to see you here. Could you do Chapter 5 Part 2 quiz? So we'll probably start, let's start with Chapter 5 Part 2, then we'll start with some Chapter 6. Chapter 5 is, so we'll do this Chapter 5 question, then should we do Chapter 6 homework, Blake, or do you want to do the quiz? A little more chill music right here as we get started. I'm going to hear this one. I don't hear this one that much. Simon Manager, getting things up and going right here. It takes so long to load sometimes. Chapter 6 quiz. Which one are you working on the Chapter 6 quiz? Let me know. We're going to do this Chapter 5 to start. We're going to do the IQ question. Here we go. The IQ question on Chapter 5 quiz. How does the question start? It says, here we go. To do the question about sample participant about percentiles on IQs. Okay. I think I found it. Here we are with percentiles on IQs. Let me mark it, and then we'll do Chapter 6 right after this. So Chapter 5, percentile on IQs. And so here we are. 4, 4 to 3. Stat to a 1. Chapter 5, Quiz 2. IQ percentiles. Okay. Let's do this. Name of Chapter 6 quiz question. We'll do it next. Okay, so we have the question on IQ percentiles. Now, we can take some guesses at this, and you might say, well, how in the world could you take guesses? If you hear the 19th percentile, is that a lower IQ or a higher IQ? Don't worry about getting it wrong, but 19th percentile, would that be a lower IQ or a higher IQ? 19th percentile, would that be a lower IQ or a higher IQ? 19th. Don't worry about getting it wrong, then I'll explain. 19th percentile, would that be a lower or higher IQ? Would it be? Be lower. because remember, the higher percentiles are on the high side of the curve. Percentile means area below. So the 19th percentile should be theoretically, and let's draw this. We always like to say, draw it out. I think it was normally distributed with a mean of 102 and a standard deviation of 11. Those are the mean and standard deviation respectively. Then we draw the curve out. When we draw the curve, we put the mean at the center of the curve. So we're going to put the mean there. And then we're going to put the standard. I'm going to check on the bunnies real quick, really quick. Bunnies are all right. There was one time that Jolly got out, like he pulled down, we have like a sheet over his enclosure, and he like pulled at it enough and pulled it out, and he like got out. So he's just being a jolly. Okay, so we have, oof, don't like that. There we go. The mean goes at the center. We put the mean. We go up 1, 2, 3 standard deviations, down 1, 2, 3. And now you can kind of figure out some of this problem by going right here and going to 90. Why is that 91? Can anyone explain just in the chat for 1,000 points, why is that 91 right there? Someone might be wondering, Brian, how did you find 91? You want to be able to do stuff like this on the test. How did we find 91 right there? These are the things you want to get good at and know how to find. These are the kind of the building blocks of our knowledge. How in the world did I find 91? Why is it 91? And then oftentimes when I draw this out, I'll put these below it. Exactly. Great job, Lindsay, right there. It's 1 standard deviation below the mean. Now, remember, we're solving this problem, 1,000 points right there. Great job, Lindsay. So we're solving this problem not just to get the right answer on my Pearson, but we're also solving to learn how to understand how to draw the curve, how to draw z-scores, because the z-scores are below it. The z-scores are normally distributed with a mean of 0 and a standard deviation of 1. So you can see here the mean of a z-score is 0. The standard deviation of a z-score is, whoops, wrong color. The standard deviation of a z-score is 1, and that's what we have going on right there with the z-scores. Now, the reason I did this is because the first question asked us about the 19th percentile. Now, the 19th percentile for the first question is actually going to be over here somewhere. And the reason I know this is because inside of here to here is 68%, which means outside total is 32 and 16% and 16%. So if below here is 16%, that makes this spot the 16th percentile. Does that make sense that this right here is the 16th percentile because 16% is below it? Does that make sense there, Lindsay, that the 16th percentile is around here? So if we had you do a test question, the test question could ask you, like, what is the, was it 19th percentile? We could ask you, what is the 19th percentile? And possible answers to it could be something like, theoretically, we could have answers like 80. We could have answers like 92.5, 104, and 118. So what would be the possible answer theoretically right here? What would be the only possible theoretical answer? And we're going to get the exact answer here in a moment, but we're just understanding the theory about this and how we could try to figure out and how we could test you on it on the test. The only possible answer right here would be what? So we did our drawing and we see the answers. So the only possible answer would be what? Out of the answers given down below, the only possible answer would be what? And then we're going to find the exact answer here in just a moment. Not 80. 80 would be all the way down here. That is actually the 2.5th percentile. So 80 is where 2.5% of the day is below. So that's the 2.5th percentile. Right here is the 16th percentile, and we're looking for the 19th percentile. The 19th percentile is what we're looking for right here. So the 19th percentile is probably closer to what? Where would the 19th percentile be? Exactly. And so do you see how I'm able to narrow this down and say, okay, that's where it's probably about. That's probably where the 19th percentile is. 80 is at the 2.5th percentile. This is where the 16th percentile is, and this is probably about where the 19th percentile is. Now, we're going to find the exact answer here in a moment, but this is how to understand it for the test. We can do something similarly with the 90th percentile. So that's our guess of the first answer right there. Let's do something with the 90th percentile here. So we're going to do the same sort of trick, but with the 90th. So if this is the top 16% right here, Lindsay, if that's the top 16%, then what percentile are we at? If this is the top 16%, then what percentile is this? Does that make sense? I'm asking right here, what percentile is this on the curve? If that's the top 16%, then this is the what percentile on the curve. If that's the top 16%, then this is the what percentile on the curve. If that's the top 16%, then that's the what percentile on the curve. If that's the top 16%, then that's the what percentile. Percentile means area below. So that's the answer to the question right there. So if that's the top 16%, then that's the what percentile. So if it's the top 16%, what percent is below it? 80. No, that's exactly it, Lindsay. You're doing great. That's exactly it. It's the 84th percentile. Exactly. So that means the 90th percentile, would it be to the right or the left of it? If this is as you just said, which you were 100% correct on, great job, that's the 84th percentile. Would the 90th percentile be above it or below it? The 90th percentile, remember we want to say 90% is below a certain point. That's what the 90th percentile means. Would the 90th percentile be above or below it? Would the 90th percentile be above or below it? So this was our first thing right here at the 19th percentile. And now we're looking for the 90th percentile. It'd be above it exactly. So the 90th percentile is probably somewhere around here. And so this is where the 90th is, somewhere around there. And so we're going to take a guess. This is just a guess. We're going to find the exact answer here soon. But I would say probably about, I'm using a little trick in my head to find the answer, probably about 115.9. That's a guess. Now, we're just going to put in these two numbers right here, or let's look at the actual numbers. So this is how to get the numbers exactly. We're going to go over to the David M. Lane, but the reason I did all that right there is everything we just did there, you don't need the applet for. So the applet's going to get us the exact answers right here. And let's go to the applet and show it on the screen. We put in the mean of 103, the standard deviation of 11. Let's double check the numbers. Mean of 102. And to do percentiles, we actually need to click this one right here, 102 and 11. So make sure you've clicked the second button. And then the 19th percentile needs to be the area below here. And the answer is actually 92.3. I'm going to pause right here. Does it make sense what I'm looking at, Lindsay? I'm seeing a curve with 19% shaded in, and then we're looking at the point right there, which is 92.3. And we can look at our answer over here and look at, we just took some guesses right here. Remember our guess right there? We guessed 92.5, and we said we'd be about right there. And that's where we were about at. Does that make sense what we drew? We drew really well. So our answer of what the answer should be is almost confirmed, and we got really close to the right answer. So the right answer is 92.3, but our guess, we said it should be about right there, and it was right about there. Is this awesome? That's what we want to see. This is the understanding we want. We also want to see how to get the right answers that it wants you to get when you put in 92.3, which it should like. Now, when we do the 90th percentile, we should see something similar to our drawing 2, and the drawing puts us right there, and it says 116.1, and we had guessed, we got close again, we guessed 115.9, so we were 0.2 off again. And if you look at where we put our mark, we said it should be right there, and it is right about there, after a little after 113. So we were able to take some decent guesses because we were looking for the 90th percentile, which is going to be above the 84th percentile, top 16%. This is where the top 10% is. And so we have this right here because we could have entered in 84, and look at that. It's right there at 113, little decimal rounding though. So the answer is 116.1. Now the last question asks for the IQR. When it comes to the IQR is known as the what? Really good review question here. The middle what? The IQR is known as the what? The middle what? The IQR is known as the what? The middle what? What is the IQR? The IQR conceptually is the middle what? Q3 minus Q1, so the middle 50% of the data, right? So if that's, what do I have on the screen right here? I'm showing the middle 50%, right? So how could I get the answer to this question for what is the IQR? Because that's the middle 50%, and down there's Q3 and Q1. So now that I have the middle 50%, we could go right here and just take these numbers and go 109.49. That's the 75th percentile right there. Subtract from it 94.581, and there's the IQR. And then we're just gonna have to make sure to round it. Let's double check all our rounding here. One decimal right here. Submit. Oh wait. I have 11 unanswered questions. Check answers 100%. Woo! Does that make sense, Lindsay? We can use the applet to tell us this answer. This one will be a lot harder if you don't know. Like if you don't have the applet, this one would not be a really good test question. I guess there are ways that we could ask you theoretically, but we haven't really done anything like that on the test in a long while. So that doesn't really go for a good theoretical test type question. But it's good to understand what you're seeing here on the applet, and that's why we want you to know how to read this, because you could have to read something like this on the test. Imagine it asked you using this graphic, if it said, what are the IQs for the 75th percentile? You're welcome, Lindsay. If it asked you what are the IQs for the 75th percentile, this would be the answer right here. We could also do things where we ask you, what are the IQs of the, we'll do this, what are the IQs of the 10th percentile? Now, this is the top 10%, but you could take and find the IQs of the 10th percentile by finding out how far this is away, because we're doing the top 10%. Let's do the bottom 10%. We could take the observation distance from the mean. There we go, 97. Subtract the mean of 102, and that means the 10th percentile is that much below the mean. So we take 102 and subtract that, and that's where the 10th percentile is going to be at. So little quick solve right there, but those are some of the tougher test questions too for people to be like, okay, wait, if we give you the 90th percentile, could you find the 10th percentile? It's just how far is the 90th percentile above the mean? Well, then take that and just subtract that distance from the mean, and you'll get the 10th percentile. So I basically said, like, well, how far is this below the mean? You could do the same here. 102 minus that value. That's how far the 10th percentile is below the mean. So that's its distance. It's 14 or 14.1 points below the mean. So then let's add that to the mean. And if you add that to 102, you'll actually be on the other side of the curve over here. And that's the top 10%, no longer the bottom, because we're just kind of flipping the curve. Really good stuff right there. And that's some of the toughest test questions right there that we just kind of briefly did right there. But people always say, well, how would I use the applet on the test? We'll use the pictures and try to understand theoretically how to do it and understand what the curve is showing you. With that, let's do some chapter 6. Which quiz question on chapter 6 are you wondering about, Blake? Blake, which chapter 6 quiz question? Chapter 6 quiz question are you working on? Drop that chapter 6 quiz question in the chat, and we'll do it. Ma Pearson, why are you so slow? Ma Pearson's like, what are you doing? Too much work. Got up early today. The World's Happiness Report. The World's Happiness Report. I haven't done this one ever. Bunch of new questions this semester. Helping my brain grow. The World's Happiness Report. I gotta find it. Got some scatterplot stuff. Love scatterplots. Horse races. The World's Happiness Report. I like the Adirondacks one because the Adirondacks are nice. Most roller coasters. I think it's going to be the last question. Better be. Okay, I got one more question. It literally is it's question 29 of 29. That's too funny, Blake. It's question 29 of 29. Too funny. Statue 1, Chapter 6, quiz. World's Happiness Report. Okay. I started to get afraid. I was like, where's the question? And it's 29 of 29. So here we go. Rather interesting one right here with what they're doing. They're doing some log stuff. I gotta talk to Terry about this because this question might go outside the scope of what we talk about. Okay, the World's Happiness Report is an annual report published by the United Nations that studies the happiness levels of individuals in each country along with the measure of well-being. For each of the 153 countries, the report provides a happiness score computed as the average happiness score of the country's respondents, individuals provided on a scale of 0 to 10, worst to best, along with a number of other attributes. Consider the following correlation table. Okay, good. It's a correlation table. Of the log GDP. So they're doing this to bring in skewed data. So sometimes when data is heavily skewed, we take the log of it. We were actually talking about this in the upper level classes today, talking about bringing in heavily skewed data. We made a really nice graphic over here. Just show this really briefly. Where's our graphic? Do we still have it with the GGR range? I don't think I cleared the environment, so I should have it under GGR range. We made a before and after transformation view, and we try to normalize data. So this was after a log 10 transformation right here. So you might have heavily skewed data that goes from like 0 to 100,000. And then when we log 10 it, the 100,000 basically by how many zeros? That would be, yes, 100,000, 5 zeros. Million is 6 zeros. So you get the extreme values are pulled in with the log 10 transformation. Along with a number of attributes, consider the following correlation table, yada, yada, and life expectancy of births across all 153 countries. So here we are with a correlation table. Now, the logging part, as The Rock would say, it doesn't matter. It's just a transformation on the variable, so we can probably find better relationships because extreme values will be outliers for QQ straight enough. No outliers. We don't want those outliers. So first off here, when you look at a correlation table, what we don't really find interesting is the numbers along the diagonals. This means happiness is 100% correlated with happiness. It's because it's the same variable. Sometimes they exclude the number here because it's on the other side. So the correlation between log GDP per capita and happiness would be this, but they just exclude it over here because the table's symmetric. They could have included, sometimes they do put the values on the other side, but this is a symmetric matrix with ones for the diagonals because it's the same variable. This is log GDP and this is log GDP, which X is correlated with X, or you could say X and Y are correlated 100% when they're the same variable. This here means there is a correlation of 0.85 between log GDP per capita and health life expectancy. So that's actually our strongest correlation right here, second strongest correlation, and third strongest correlation. There's only 3 correlations really to look at right here. Once again, these are excluded because they would just be the symmetric version on the other side. If there was a number here, it would be 0.77 because it's health expectancy and happiness. You would just be looking at it as XY kind of reverse, which would be the same correlation. Okay, so now we understand what the output is showing us. Is log GDP per capita more strongly associated with happiness or life expectancy? So log GDP per capita, and we want to look at happiness right here, and log GDP per capita, health life expectancy. So the strongest is log GDP per capita with health life expectancy. The correlation between, where's health life? The scatter plot. Without scatter plots, no. The correlation between log GDP per capita and health life expectancy is higher. So GDP per capita is more strongly associated with, yes. Let me look at the without scatter plots. Yeah, they're getting it right here. Without scatter plots, it is uncertain that the underlying relationships are linear. If they are linear, then the log GDP per capita would be more strongly associated with happiness. Well, it would be nice to have scatter plots, but there is a higher correlation. Yeah, it could be an extreme outlier, but I think A is what I put last. Well, for certain, it's health life expectancy because it is more strongly associated. But I think what they're getting at right here, without the scatter plots, there could be an extreme outlier. So we have to watch out. Because if we're saying that there is this sort of relationship, we'd want to look at linearity, which is a huge underlying assumption. So without scatter plots, it is uncertain that the relationships is linear. That is true. That is a fact. If they are linear, so if they are, then GDP log per capita would be more strongly associated with health life expectancy. And the answer is found right here because of this. One of the key assumptions, exactly. And so one of the key assumptions, thank you, Blake. One of the key assumptions for correlation is that there is a linear relationship. And we were talking about this a lot yesterday, that when we do correlation, we have to understand the form of it, and it needs to be linear. So we are looking at linear. You'll see linear throughout this. So if we're not doing linear correlation, we could run into problems, and linear is the form. So I do agree with them, and I see where they're going with this. You really need to look at that scatter plot, which is one of the first things we do when we look at data is we look at it. Does the report provide evidence that improved health would result in greater happiness? We can't say causation right here, and we'll get to this in this chapter. So no, because the correlation, no. You can never conclude causation. Correlation does not prove causation, even if it's 100%. You would say, well, why would correlation of 100% not show causation? Well, take a look at this. If you have 2 points, the correlation of 2 points will always be what? Or what? The correlation of 2 points must be what or what? The correlation of 2 points, which would probably have more than 2 points, 158 it said or something. But the correlation of 2 points when calculable will always be what or what? The correlation of 2 points, because correlation tells you direction. Well, this one's positive, this one's negative, but if there's only 2 points, then it's perfect, right? A line would perfectly go through it. So if a line perfectly goes through it, the correlation must either be positive what or negative what. With only 2 points, your correlation would either be this or this at all points. When it's calculable, there is the instance of no variation in y, which then you can't do correlation because there's no variation in the y variable. The correlation would either be positive 1 or negative 1. Does that make sense, Blake? The correlation with 2 points only would either be positive 1 or negative 1. So this is not really that important because 2 points always have a perfect line going through them. They always have a perfect linear relationship. So that's perfect positive correlation, perfect negative correlation. But as The Rock would say, it doesn't matter. It's just going to be that way for any 2 points. Does that make sense here theoretically? So even if correlation is really high, we can't say it shows causation because you just take 2 points as long as they're not completely flat and they're going to have perfect positive or perfect negative correlation. And that doesn't mean causation. So we should get everything right here. Pretty good question. One of those new questions. Yeah, that's what I thought. Yeah, I realized where they were going with this first one right here, which I do agree with, because you could have some sort of extreme outliers. So they're right. We want to make sure that we are properly applying correlation to linear relationships. So you should look at the scatter plot to begin with. And if the scatter plot showed there was a linear relationship, then this is the strongest relationship. You just have to make sure you don't have like an outlier that is going to massively impact the relationship. Really good stuff. What other ones should we do, Blake? That was a great question, and try to understand the theory right here. Try to understand their output, understand what the correlation matrix is showing you. You don't want to just look at the answers. You want to understand what is this output? What does it mean? It is the correlation between all of your variables in your data set, telling you the strongest correlations and the weakest. Down the federal office. Oh, let's do it here next. The Office of Federal Housing. I think I saw one recently. All the new questions. The Office of Federal Housing. Found it. Let's go check it out right here. Where's the timestamp? 29:13. Here we go. Let's do it. Okay, the Office of Federal Housing looking to do some correlations right here. The Office of Federal Housing Oversight collects data on various aspects of housing. Here's the scatter plot of the housing index cost and median family income for a subset of the U.S. states. The correlation is 0.65. So that's a moderately strong. The closer it is to 1 or negative 1, the stronger it is. 0.5 is kind of moderate, and 1 is perfect. 0 is the weakest it can get. So when you look at this right here, mostly linear. So what I'd do over here is we'll hear this more next class. We'll hear some QQ straight enough. No outliers. Plot doesn't thicken. For the next one. So is it straight enough? Yes. Is it strong? Decent? Are there outliers? I don't really think those are outliers. So I would say this is a quantitative relationship, which is required for correlation. It looks to be straight enough, and I don't see extreme outliers. So I'd say this is pretty good. So 2 quantitative variables to do correlation. You have to have that. Is it a straight enough relationship for linear correlation? It looks straight enough. And are there no outliers? Doesn't look to be outliers. Describe the association. There is, okay, look right here. I don't think it's, oh, and it's not linear. Haha. A, B, C, or D. A, B, C, or D. So this right here literally tells you the direction. A, B, C, or D. What do you think? I think this one should be the easy one. No association looks like a plot where we have this right here. This is an association, but not linear. Moderate positive is going to be correct. So moderate positive, if this one didn't say, but it's not linear, we might have a little bit of, I don't know, but it is mostly linear. Does a line go through the data? It looks to go through the data mostly. If the variables were standardized, what would the correlation be? Now, we really did some great work on this yesterday. I think I closed it out, but we did some theoretical work on this because if you take data right here, and let's just do a theoretical question, we're going to just take numbers. These are random numbers. So 100 random numbers, and y is going to be the numbers 1 through 100. Let's plot this. So let's plot y comma x. Does that make sense what I've plotted right here? Good to see your meat. Does it make sense that I just have random x numbers and y is numbers 1 through 100? I just have a plot of the data. Does that make perfect sense? Does that make sense right here? Like, how does that sound to you? Is it just random numbers? Makes sense? And now let's watch this. You ready? What if I were to take and scale my y variable? What just happened to that plot? Y got turned into z-scores also. Do you see any difference in the data? If you scale your data, what happens here to the data? If you scale your data, if you were to turn it to z-scores, what happens to the data? If you scale your data, nothing. So what would happen to the correlation between x and y? Right now, there's a correlation of 0.13 right here. What would happen to the correlation? If I scale it, what happens to the correlation? Nothing. Here's the correlation of 0.13. Here's the scaled. It's the exact same. Here's the plot of the data, or we just saw it. There's the plot of the normal data. There's the plot of the scaled data. Doesn't do anything to it. So what would be the value of correlation if both variables are standardized? What's going to happen to correlation? Because correlation is unitless. Correlation doesn't worry about your units. So what would be the answer to this question of, if you standardize correlation, what happens to it? Or what would be the answer? Because correlation is 0.65. It turns the x and y into z-scores. Yep, that's what standardizing means. So it's going to just be 0.65. And that's what the scale function does right here. You can take values and run the scale function, and then they all become z-scores. And you can see right here at the center, it's 0. It's going to try to make those, it's a uniform distribution, so it's going to have trouble, but it's going to turn them into z-scores. So standardizing means z-scores. Yes, good answers, Blake. Excellent work. Median family income had been measured in thousands of dollars. How would this change correlation? So if we had measured it differently, but it's still just the same variable, what would happen to correlation? What would happen to correlation if we measured it differently? If we were to say, now let's measure same sign, yeah. So the correlation would have the same sign and the magnitude would not change. Suppose Washington, D.C. has a housing cost of, okay, now this is going to change it. Suppose Washington, D.C., which is going to be one of these dots right here, has a housing cost of $548. Is it that point over there? And a median income of $45,000. I think it's this point right here. If this region were to be included, okay. So it's saying that's a new point in our data set. So 548 and 45,000. So it's going to be right over here. So let's look. It's asking if you include a point here. So that's our data. If you include points inside of here, it gets stronger. Things that follow the, I would say, well, this one is including a new point. So we're adding a new point to the data set. We're not changing the scale of the data or standardizing it. We're adding a new point. So the further you are away, it might actually at some point get weaker. The exact point would be hard to determine, but it's usually like a radius outside of this, that outside of here, you're going to see it getting weaker at some point. There might be a no change point where it really wouldn't impact it. But at some point, like if you go over here, this is definitely weaker. And over here, this is definitely weaker. And then you might even flip signs. But if you have something far away from the linear relationship, a new point added to it, it's going to make it weaker. Does that make sense? What's going to happen right there? I don't think it's going to change the sign, but it's going to pull it outward. And I can probably best exemplify this. Let me show it with this right here. Watch this. Core demo. Please work properly. Core demo. Nope. Undo. Let me end this. Let me exit. View. Actual size. There we go. Core demo. Run it now and check it out. Okay. So here is what our data looks like. Does this make sense, Blake, right here? We have a correlation of like 0.65. We have 0.65 as our correlation. I'm trying to get to 0.65. There we go. Our correlation, good to see you, Meredith. Our correlation is 0.65, and you can see it up here. And then we're adding a point over here. Just look at the graphic we created. We're adding a point right about here. So this point's further away from the cloud of data, and the correlation dropped. Without the red dot, it was 0.65, and with the red dot, it's 0.54. But if you were to add a point towards the linear relationship, correlation will get water if we add it towards where the line would be going through the data. If it follows the linear relationship, because this is linear correlation, the correlation would get what if we added something like over here, which is where I can see a line going through it. What will happen to correlation now, Blake? If we add something towards where the line would be going through, correlation will get water. If I add it where the line would be going through the data, the correlation will get water. Here's the correlation now, and if I add a new point where the line would be going through, the correlation will get water. Stronger. Did you see it went up? So without the red dot, it's 0.65. And if you add another point down here, it's going to get even stronger because this is kind of creating a better linear relationship. But if you add a point way outside of here, it's going to get a lot weaker because that pulls away from the line. So you want the line to go through the data and well describe the data. So when points are far away, it makes it weaker. So points inside of kind of a density cloud, it's hard to tell exactly like, yep, they're good. I was trying to figure out where it would be. I've done too much of this, but this is where it really is not impacting it. And then over here, you're going to start to see it. Oh, still not impacting. But at some point, it's going to start to make it weaker. And the further out you go, the weaker it's going to impact it. So there we go. You see, go a little bit more further over, and it keeps getting, oh, that was stronger because that's going back towards the line this way. So if we go down towards where the line would be at here, we're on kind of the line. So it's hard to tell exactly, but it right here, going to get weaker. And that's where we're at. They're putting it towards the center. Good spot to put it to know it'd be weaker. So it would have the same sign, but correlation would decrease. Do the data provide proof? We don't like words like proof in statistics that raising the median family income, the cost of housing index will rise. The data do not provide proof since the value of the correlation coefficient cannot prove any causation. We should get everything right. Woo! A little bit fair on that last one. They're once again just hammering home the point that correlation is not causation. So once again, it doesn't matter how strong the correlation is. You can't show causation. How are we doing on this one right here, Blake? I hope we've added a little bit more to your theoretical understanding by using this right here. For assignment 4, do we use the survey data frame? I think so. You can meet, oh yeah, 320. So you can use any data frame for the assignment 4 meet, any data frame. I think the grader's getting caught up. I need to talk to them. Super helpful. That's what we like to see. Remember, we're here to learn the topics, to understand how to do them. Speed of cars? Yeah, let's do speed of cars. You got it, Meredith. You got to meet. Yeah, ask those questions away. Keep asking them. Increase font size. Core demo. Good stuff right there. Speed of cars. Chapter 2 quiz. Part 2. Speed of cars. Step 201. Chapter 5 quiz 2. Speed of cars. Brian, can cars go over 300 miles per hour? I bet the fastest car has. You like drag racing cars. Fastest car speed record. 763. I was like, I mean, your general car's not going to do that. 304? I mean, drag race cars. The current holder of the outright world land speed record is Thrust SSC driven by Andy Green, a twin turbojet, blah, 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 on October 1997. So that's a while ago. Can we get the result from this if there's time? Well, I'd have to do a different one because I don't want to interpret yours. But that looks correct right there. You're explaining someone's GPA based on. I'll do one. Meet, you got it. I'll do a unique one to us. That way, and you don't want to do the ones I do. So let me put it right here. Assignment 4. Good to see you here, Andres. Association output. Okay. Let's see. We need to get chapter 5, speed of cars. Oh my gosh. One of these days I'll sleep. I was watching The Resident, and like someone on The Resident was like, I haven't slept in days. I mean, I sleep, but I just need to sleep more. Get sleep. Your body needs it. Speaking to myself right here. Where's the speed of cars one? Compensation logged in SAM? What? What's that? Speed of cars. Companies. All these instructor tips. Wait, speed of cars. A traffic engineer. Okay, traffic engineer. A traffic engineer. Okay, let's check this out right here. It has a normal probability plot and a histogram. I think so. Let me see if there's the right one. Is it? Well, no, wait. This one has a traffic engineer. It doesn't say anything about normal probability plots. Might be a different one. How's the question start? Different one? Okay, good. Let me find it. Speed of cars. Found it. Speed of cars. Cool. It does start at speed of cars. You're right. Thank you so much. Let's throw 1,000 points. Yep, definitely tell me, because I was like, yep, doesn't have that. And yeah, know what a normal probability plot is. Great job right there, Meredith. Thank you for asking. Keep asking those questions. We got a lot of time right here. I think we don't have class till 55 minutes. Grab a snack between, but got a lot of time to do some work. So much room for activities. Let's do this. Okay, we've got speed of cars was measured as they passed one point on a road to say whether traffic speed controls were needed. Below are the histogram and normal probability plot, which shows us the plot, that is the probability of a distribution being normal, of the measured speeds. If a normal model is a normal model appropriate for this data. So really, when you look at this, what do we want to look at with a normal probability plot? So when you have your data, you can make a histogram of your data, and your histogram might look like this. But what is the point of a normal probability plot? Does it go straight through that? The red line here is what a normal should look like. And generally, you want to look for things. If we're going to quiz you on when it doesn't look good, we generally want to see things like this is going to be a really bad one. So this is a bad one, indicates right skew. So let's go plus title right here and say skewed data. Skewed / or we'll say not normal. So this data right here is not normal. And this is follows line is normal. So following the line means that it's normal because the red line is what a normal should look like. So this is kind of like a guideline right here telling us if your data is normal, it should generally follow the line. Now, it doesn't have to perfectly follow the line, but let's think. Does this generally follow a line? Now, there is an outlier over here. There's one outlier, which is showing up right here on the end of it. But does it generally, and I'm going to be super mad if they don't agree with me on this. Bob Pearson, you better agree. I'll run a Shapiro-Wilk omnibus test on this. Does that generally follow the line? Generally. You thought so? Is it going to tell me I'm wrong? Is it going to be like, no, because of the one outlier, it's not normal? Yes, the histogram, even though, yeah. So, well, the little tiny hump is that one data point over here. So that's just a little weirdness. I'm 99% certain on this. Yes, the histogram is unimodal and symmetric. That means normal. And the normal probability plot is straight. So unimodal symmetric. I was about as sure can get. If they had told me I was wrong, I would have been mad at my Pearson. I've been looking at normal probability plots for a long time. Meath, I bet, knows about some more normal probability plots. Hurricane Katrina, yeah. That's another standardizing of data one. Let's see, I think we're doing a little 320. Drop those 201. But here's the thing, 201, hang out here for a moment, because we're going to do something that actually coincides with what you're doing here. Let me take this down here, Blake. Thank you so much, Blake, for all the questions. Chapter 6, quiz, Hurricane Katrina. It's like a long time ago now. Hurricane Katrina's force winds. Okay, let's do a little 320 and go back. So 201, if you're still hanging out, check it out. We're about to analyze 320 output, and you're about to hear some of those same topics we've already been doing. So here we are, 4523. Let's do it. So A correlation is a specific type of association. We're not going to be doing correlations right here. We're going to be doing analyzing differences between means and medians. But we have a really cool function in 320 called the associate function, which is inside the reg class package. So you have to have reg class loaded up or else you won't get the associate function. Now, once again, I'm doing don't do Brian's example. You don't have to do this. So don't do my examples. Please just don't turn in like the exact things I do because I want you to do your own examples. So please don't do the exact thing I do. I'm loading the body fat data set. The body fat data set right here has people's body fats. And what does this look like to people? If I show you this, have you ever seen something that looks like this right here? What does that look like to you? If you're in 201 or 320, we just say that that looks like you're just looking at what right here? Like if you see that, you're just like, oh, that just looks like what? This is the body fat data frame. We call it a data frame. It's got 252 rows. It's got 14 columns. The columns are the names of the variables. We measured people's body fat, their age, their weight, their height, their neck measurement, their chest measurement. So these are all the measurements. And this just looks like a what? Like I'm currently viewing this thing right here. I'm looking at it right here. So that just looks like what output to you, or just looks like a what program. You ever see a program that looks like this? Just a spreadsheet, right? It's just Excel spreadsheet. Great job, Amanda, right there. It just looks like an Excel spreadsheet. It's just Excel. I mean, might as well be. We could export it to CSV. So you could, if you want to bring it to Excel, you could go write.csv body fat, and then do body fat.csv. And there you go. Now you've written it to your computer. You could open it up in Excel, and now it's an Excel file on your computer. We don't need to do that though. Okay. So now you don't have to do this step with your data. I've seen a few people doing this. The reason I'm doing this is because I don't have a variable that is categorical in this, and this assignment requires you to use categorical data, so you don't have to do this step. So I'm going to go here to if else body fat data frame age is greater than or equal to 41, then the person is old. Oops. Nope, still. There we go. And if not, young. So I've classified people as old and young right here. Now I'm going to go and make this into a factor. That turns it into a categorical variable. And then I'm going to store this as X just for safekeeping. Now that I've stored it as X, I'm going to go to my body fat data frame. I'm going to store here age group. You don't have to do this because your data set should have categorical variables. But by doing this, I've appended onto it the age group vector. So you can see we now have a categorical variable with 2 levels on if someone is old or young, which is going to be a requirement to do this because we're analyzing things by groups and seeing if we can compare them right here. So what should we compare between old and young people? Yesterday we did body fat, and I can't remember what else, but what other measurements should we compare between old and young people? So what other measurement? We're seeing if someone's age group can explain why something else is happening. So what other measurements should I compare right here between these people? We'll go data equals body fat, let it autocomplete. And what other thing? We'll do seed equals 320. What other things should I do right here? What other group should I do? What other group should I do? What other variable? So I should see if age group explains somebody's what measurement. We can even do like, let's change the age group. Let's go here to 51. Let's go to 50 actually. There's the old and the young now. And let's see if age group explains somebody's, let's see their biceps. Does somebody's age group explain their bicep measurement? And so we need to go biceps and run this. Figure too large for margins. That means we need to increase this over here. Make it really big. And now let's run it. And here we are. Here's the output. Anyone can tell me what this graphic is called? You get 1,000 points. What is this graphic called right here? What is this graphic called down here? What is this graphic called? We just saw it a second ago in 201. What is this graphic called? Normal probability plot. And there's only one outlier over here. I wouldn't use medians because this is, it's kind of a scatter plot. It's the normal probability plot, which we were seeing in the previous question. Remember from 201, we were seeing, we have it closed now. Good questions right there. And Blake and Meet, 1,000 points. So the normal probability plot is going to be looked at first right here because when we do this, we need to say, are we going to analyze what's or what's in this output? When you look at this output, you're asking yourself, am I going to analyze the difference between what's or what's? Am I going to analyze the difference between what's or what's? Am I going to analyze the difference between what's or what's? Well, yeah, if you're using medians, you would use this right here, but which one should I use, means or medians? If we're using medians, we should do that, but what does this conclude right here? There's only really one point that escapes, and you can look at the histogram secondary, but that's really good right here. Should I use means or medians? Like, that's what we would look at first. Is we'd say right here, does this follow the normal or not follow the normal? So should I use means or medians? It's roughly normal. Exactly right there, Meet. That's the perfect answer. It's roughly normal, so we would use the means. So now, if you were to choose medians, you would look at this output, and you would look at this output here, but we're using means. Now I'm going to show you a trick. If your interval is not conclusive, you would do what? Increase what? If your interval, I'm going to show you a trick for this to get the right answer. Don't go below 50. Maybe I'll be nice. Don't go below 20 because I think I have to, yeah. If your interval is not conclusive, because we're looking at the interval down here, this is a conclusive interval. You have to increase the permutations. So what would happen if I were to decrease the permutations? If I were to do less permutations, because this does 500 by default, so it did 500 permutations for me. I can confirm by redoing the output and doing the 500 permutations and seeing the same interval right there. So if I were to decrease the permutations, my interval would do what? You shouldn't just generally do this, but I'll let you do it to get an answer to help out the assignment, because now if I decrease the permutations, what would happen right here? So you can find one of your required things by doing this, because it might happen now. We'll see if it does it for mine. We'll look at the output afterwards. Don't go below 20. Going below 20 is a little, it's ridiculous to do 20 even. 500's your good default. But what will happen to the interval down here if I decrease the permutations? Well, we're doing less estimates of what the p-value is. So if you do less estimates, the interval will get wider. Usually we increase it. But to show a theoretical idea, we could, well, if you increase it, the interval gets smaller. So if you decrease it, the interval gets wider. It already ran it. Ooh. See, I didn't get a not significant. It did get wider though. So if you decrease the permutations, it gets wider. Here we'll go right here and we'll do height measurement. That's mad about the graphic again over there. Aha. Why is this interval inconclusive? Why is this interval here inconclusive about the significance of the test? Why would we say this test, analyzing differences in heights between these groups, which is accurately looked at by analyzing, ooh, we got an extreme. Now this one's iffy. Do you see the extreme outlier? This is iffy now. And it is inconclusive, but we might actually say we should maybe go with medians because there's an extreme outlier of somebody who registered at 28 inches. I'm wondering if that's a typo. Because that is among the shortest individuals in the world. So we either need to exclude them or we would need to go with medians. Does that make sense, Meath? Like if we're not excluding them, I'm going to go with medians. So we actually did find a medians test here. Because of the extreme outlier down here, I would be analyzing the difference in medians, which does mean you're looking at this output here to interpret these differences. So I would definitely be looking at the medians difference right there. So how could we make this interval to be a conclusive interval? So the medians interval says that it is inconclusive in its result on if the test is statistically significant. And how could we make this a conclusive interval now? What could we do with this result or this function right here to make it more conclusive, possibly more conclusive? What do we do? Read the bottom of the output right there. Increase permutations. We go to 200, rerun it right here. And now the interval is conclusive. Remember, we're using medians because of the extreme outlier. So now we think the p-value is somewhere probably between 0 to 0.018. We could do 500. Yeah, any which way. It's now going to be conclusive, and now we run the results. And you'll notice right here, the interval is conclusive in its result. So that's what we want to go towards. And we want to know when to use means and medians. Then we'll look at the proper output, then make the decisions. Is it making sense what this assignment is, Meath? Like what you're doing right here, what you're analyzing, what you're going to put forth, and how to explain this output and to talk through it. So yes, awesome. So make sure you do 3 relationships that follow it, and don't use my examples. I think if you look at yours, you want to be like, okay, should I be using means or medians? And then is my interval conclusive down here? The whole thing is about reading this output, like understanding what it means theoretically, every single value, and then to talk about the differences right here if they're meaningful. Even though, I mean, I don't know, it's a difference of about 1.75 inches between the median young person and the median older person. So maybe we might say there's decent evidence to suggest that older people are a little bit shorter. Maybe there might be some sampling bias here or something, but there is statistically significant difference. The difference is 1.75 inches between the medians. This shows that the discrepancy we observed was 10.3 times larger than we would have expected due to random chance. So I think there's something going on right here that older people are generally a little bit shorter than younger people. We analyzed medians because of the extreme outlier to not let it impact the young group. So you'll notice right here, well, the data is probably a little bit skewed. Either which way, it's about it's 1.3 inches. I don't know. It's 1.3, 1.5 inches. Both are statistically significant, but I would go with medians because of the extreme outlier. With that, it is time for more data analytics. Okay. I think we had another question right here. Time for at least one more. So we care about, I'd say maybe, yeah, kinda. I kinda care about them. So you can be like, these seem kind of important. Like, it's small-ish. I mean, like 3-4 inches would be more, but remember, you can just be descriptive. You don't have to be a complete yes or no, because the company's like, do we care? And you'd be like, yeah, it seems kind of important. Not super important. I kind of care. Is it really important? No. Is it maybe important? Yeah, ish. So you can use, you can use kind of vague terms, like be more vague with it. Does that make sense? You don't have to be like, I am confident that this is super important. It's just, yeah. So the biggest thing is to like know that practical significance is all just opinion. It's all just opinion. Do I care? A little bit, a lot, some. It's all just opinion when it comes to practical significance. It's the hardest one because you have to make a case for it. Quote the numbers. Quote the numbers. With that, let's start this up. Okay, we've got some Hurricane Katrina right here. So Hurricane Katrina's force winds exceeded 120 miles from its center. Katrina was a big storm, and that affects how we think about the prediction errors. Suppose 120 was added to each of these to figure out how far that prediction track we might still be from the wind damages. Explain how that would impact the correlation between prediction error and year and why. So I think the best way to understand this question is to talk about test scores. So if you were to go here and we looked at people's test scores and we looked at how long they studied for the test. So we have here your score, and we have here your study time. So if we were to take the score and the study time and plot them, we might see study down here, score over here, and then let's try this. Let's try this. Boop, 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 boop. Almost. Darn it. Good. Okay. So there is a what correlation between someone's score and their study time? Someone's score and their study time is whatly correlated. Just look at it visually and look at what direction it goes. Somebody's score and their study time is whatly correlated. Look at the direction. Somebody's score in their study time is positively correlated. Great job, Amanda, right there. 100 points in the chat. So now watch this. I'm going to take everyone's score and I'm going to add 10 points to it. What do you think happened to the correlation when I added 10 points to it? Remember, it was down here like this, and it looked just like this. And then I moved it up here and said, let's add 10 points to it. So what happened to the correlation when I added 10 points to everybody's score? What happened to the relationship between study time and score when you just add a constant to someone's score? Look, if you had the highest score on the test, that's you right there. Well, then if we were to look where you were previously, you would still be the highest score. We just added 10 to everybody. Nothing. Yeah, you got it. Exactly. Nothing at all.
It doesn't matter.
It doesn't matter. It's going to be the same correlation. So did the sign of correlation change? No, it would not change. They're doing the same thing. They're just adding a constant to it. And the magnitude of the correlation, which is how strong it is, would not change. Because what is correlation based on? Correlation is calculated using what's? Correlation is calculated using what's? Correlation is calculated using what's? What do we calculate correlation with? Correlation is calculated using what's? And these are unitless. Correlation is calculated using z-scores. Yup. Great job, Blake, right there. They're calculated using z-scores, and since we calculate them with z-scores, the z-scores wouldn't change if everyone got points added. So the z-scores, which the correlation would not change. If the z-scores did not change, boom, nothing changed. So just adding a constant to the correlation would keep it with the same sort of structure right here, that your study time would have the same correlation to your score, because still those people who study more got a higher score. I just increased everyone's score, but the average score would still have a z-score of what? Look, if you were the average score here, you would have a z-score of what still? If you were the mean, so you're right there at the mean, you would still have a z-score of what if I were to increase or decrease people's scores? If people's scores are increased or decreased, oh no, it almost works so perfectly. Where's the mean? Oh, there it is. You would, if I increase your scores, you still, if you're at the mean, you still have a z-score of what? You would still have a z-score of what? If you're at the mean, if you're that red dot right there, and I increase or decrease scores, your z-score, if you're at the mean, would still be what? So hopefully visually this, someone's like, oh, you still have a z-score of 0. Traffic engineer, sure, Meredith, let's do it. So that's what's going on here visually, is if you are at the mean, if I decrease all the scores, it's still the same correlation, because it's still the same relationship between study time and score. So you still have the same z-score, so it's going to get mathematically calculated out the same way when we do the calculations for it, and it gets turned into a z-score. Is that chapter 5, Meredith, right there? That's chapter 5, right? Just let me know. Chapter 5, right? Traffic engineer, chapter 5. Thank you so much, Meredith. It was the one we were going to do previously, right? Let's do it. Ooh. Oh my gosh. Gonna make everyone yawn. Chapter 5 is quiz. Traffic engineer. You bet. And getting it going right here. Thank you so much, everyone, for being here. It's about that practice. Getting these hundreds is really a great way to do well on the test, because there is a high correlation between your homework score and your quiz score and how you do on the test. It's just practice. I mean, that's I can't promise you'll do well on the test if you do as many questions as you can, but you're just practicing. And then if you don't do well on the test, which is not fun, you've got some grades to help you out. You've got some good grades. So, the more you do, the better your grades. And it helps out if the test doesn't go so perfectly. Because it's a tough test. It's a tough test, and we're going to practice a lot. So let's do this right here. Let's do the chapter 5 traffic engineer question. Let's do this. Okay, it's time for some chapter 5 traffic engineer question here at 104, 23. Let's do this. A traffic engineer recorded the speeds of cars driving past their house, where the speed limit was 20 miles per hour. So they expect that. The mean of a sample of 100 readings was 23.82. So there's their mean with a standard deviation of 3.62. So here is a view of the sample statistics. Okay. What they're going to try to show here is the shape of the data. We have a min value right here. We have a max value right here. And just looking at the distances, this is kind of symmetric. There's the 90th percentile. That's further away. So there's a little bit of right skew, a little bit. It's not so crazy. Using a normal model, what value should be in the middle 95%? Now, pretty sure they're going with the empirical rule right here. If they don't go with the empirical rule, I'll be a little unhappy. But the exact z-score is 1.96. But what should I do if we're using the empirical rule for 95%? If we're using the empirical rule for 95%, what should I do? When you hear 95% with the empirical rule, what should you do? When you hear 95% with the empirical rule, what should you do? You should go up and down what? Draw it out. Yep, exactly, Meredith. Draw it out. We like that there. 1,000 points, Meredith. Keep up those answers. We draw it out. And you can draw this on a sheet here. We've drawn a lot of them today right here. So if you look at all our different drawings, we've been drawing them out somewhere here. There we go. There's one of our drawings earlier. And when you hear 2 or 95, you should think 2 standard deviations. So you want to go out the 2 standard deviations. Now, practice drawing these things out. You can also use the applet to get the answer. So using the applet, we're going to go, and the applet is in the chat link, or the link is in the chat, rather. And we're going to go right here and put the mean of 23.82. Standard deviation of 3.62, and then we could do it here, but it's going to be easier if we go over here. Forgot which one to go to. 95%, or we can just view it. What am I saying? We can just look at it. So if we put in the numbers, and it changes them, let's reload the page. We can just look at it. 23.82, 3.62, and there's the answer right there. 16.58 and 31.06. So 16.58. And the other number is 31.06. Should like those. A study comparing the effectiveness. I'll take a look at that here soon. You got it, Blake. So all I've done is go up and down what? What have I done to get these answers? How did I find those answers right here? What did I do to find 95%, especially for the test? Because we could draw this out. I went up and down what? Part 2 is tripping you up. We'll find that here in a second. You got it. I hate that doesn't sometimes draw that third. To find those answers, I went up and down 2 standard deviations. Exactly, because that's the middle 95% is within plus or minus 2 standard deviations on the curve. I don't think it's going to want the decimals. If it did, 3.62, 3.62. It could possibly want the exact answer, which I'm hoping it doesn't want. It might also have the empirical rule, but these are the exact answers right here using the exact calculations. The middle plus or minus 2 standard deviations is actually 95.449. This is the exact answer. I think we're good on this. Hopefully they're nice about it. We'll find out. The accompanying table lists some summary statistics from your part in answer A. How well does the model do in predicting these percentiles? Are you surprised? The cutoff for the middle 95% is actually where? So when you think about the middle 95%, what percentiles would we be at? This is a really good question. I love it so far because the middle 95% is the what then what percentile. So let's look at where the middle 95% is. It's at the this percentile and it's also at the this percentile. Where are these percentiles? The middle 95% is at the what percentile and the what percentile. And I'll give you hints by drawing this right here. Not close. That would be the middle 90%. So here's a hint of the areas below. So where are we at those question marks? Good guess, Meredith. 97 point. Exactly, because when you're at this point right here, by saying this is the 97.5th percentile, finish my sentence. That means what, Meredith, right there? By saying that's the 97.5th percentile, that means at this point right here, there is what? By saying that is the 97.5th percentile, that means at that point, what? And you can see it if you add across the arrows. That means what for that point? 97.5% of the data is, because it's percentile, 97.5% of the data is what to that point? 2.5% above and 97.5% below. Exactly. Percentiles are generally thought of as below. You can also, I'm throwing 1,000 points, great answers in the chat. There is 2.5% above, but then also we think of percentiles as below. When you give the number of the percentile, when you say this is the 2.5th percentile, it means 2.5% of the data is below that point. So when you give the number of the percentile, it means the amount below. So when you look at the percentile right here, we have 16.87 for the this one, 16.87. Don't make a typo. 30.84. Was it 30.84? I don't want to double check that one. 16.87, 30.84. Good stuff right there. which are, how close are those? Yeah, I mean, what do you think about those numbers? I mean, these things aren't, it's not perfect. It's not perfect, but I mean, if I told you I'd give you $31.06 for something and I gave you $31.84, you'd be like, yeah, that's about right. It's about right. These numbers here kind of match. They're close. You see, it says very different. These aren't not very different. They're close. They're close too. The predicted values since the distribution. So if it is normal, it's going to match. Since the distribution is approximately normal. Did they say it's approximately normal somewhere? If it was skewed, it wouldn't match. So if it's approximately normal, we should not be surprised. So it should say if the distribution, given the distribution is, or the distribution was normal. I wish they said up here it's normal. I don't think they do. No, but if it is normal, then the numbers should match, and we are not surprised. Boom! That was an excellent question. I love it. It used the empirical rule. It had you look at percentiles on the curve. Really good. Hey, Noah, good to see you here. Let's throw 1,000 points for a random Noah in the chat. Good to see you, Noah, and thank you so much for all your help on the Discord and everything. If people, people want to tag you, you're welcome, Meredith. Do we have time for one more? Do people have another one? This was a really good, tough question. I can see where this one would be pretty tough. And then understanding, we're talking about what should it look like if it's normal, what should we expect. We did a little bit in the David M. Lane, but once again, this shows that you don't need the applet to solve it. I could have found these numbers right here by going to the mean and adding 2 standard deviations. 3.62 times 2 plus 23.82, and there's the number over there, 31.06. But did I type it wrong? 3.62 times 2 plus 23.82, and there it is right there. I did make a typo. That's why sometimes it's easier to just drop it in there. So you could find both these numbers. The lower one is found by subtracting 2 standard deviations. So times 2, take that number and do 23.82 minus that, and there's the lower number. So once again, I just want to show that you don't have to use the applet at all times. We could draw it out like we've been doing, because drawing it out is going to be a great way to practice these problems and make sure you understand it. Can we finish the effectiveness of several antidepressants? Chapter 6, right? The effectiveness of several antidepressants. Chapter 6, right, Blake? Let's do that. Let's finish off with the effectiveness of many antidepressants. Stat 201. Chapter. Yes. Nice job, Blake. Good job working ahead right here. Chapter 6. The effectiveness quiz. The effectiveness of many, there we go, antidepressants. Okay. Chapter 6 quiz coming right up. Good job. Just practice these problems. Understand the theory behind them. It's not just about those answers. We're here to understand how we get the answers. Okay. Oh my gosh, there's so many questions. With the disk drives. Some easier ones like some true false. Where is it? Yeah. It's gonna be like number 25 or something. Like, we're on question 17. Oh wait, a study compared, right? A study compared. Found it. A study compared. Okay, got it. Yes, awesome. 114.43. Let's do this. Okay, we're looking at a study that compares the effectiveness of many antidepressants right here. And take a look. We want, when we compare or when we analyze quantitative relationships, and we got 2 quantitative variables because this is a scatter plot, for there to be a straight enough relationship to do correlation if we're going to assign a value of correlation to it. The scatter plot right here definitely indicates a linear association. These aren't really outliers, just a little weirdness. That's fine. Mostly awesome. If those points were to move a little bit up, it'd be amazing. It's a really good, strong correlation. So it is appropriate to calculate the correlation because the plot shows a positive sign. I don't like that it says positive sign. That, as The Rock would say, it doesn't matter. Linear form is the most important. So I'm a little bit scared right here. And I don't know why they have multi-select. Oh, yeah, they do. Why would they do that here? It's a new question. It is not appropriate to calculate correlation because the variables are both qualitative. Is that what they're getting at? Is that what they're getting at? No, it looks like it's quantitative. Let me look at the question again. Each of these experiments compared the active drug with a placebo. An inert pill, we know, placebo is an inert pill, it doesn't do anything. Each experiment, some patients treated with the placebo had improved a phenomenon called the placebo effect. Yes. Patients' depression levels were evaluated on the Hamilton Depression Scale, where larger numbers indicate greater improvement. Hamilton scale is widely accepted standard that was used in each of the independent run studies. The scatterplot to the right compares a mean improvement level for the antidepressants and placebo for several experiments. So placebo improvement versus drug improvement right here. So we're looking at it's quantitative. It's not appropriate because there's an outlier. It's not really an outlier. It's not appropriate to calculate because the trend's not linear. It is linear. If they are going with something, it's going to be this, but this looks to be drug improvement. It's a quantitative scale. See, then they're doing correlation. So yeah, it has to be. This is weird the way they phrase it. It doesn't matter that the plot is positive. That's not. It's important that it's linear, quantitative variables. Let's repeat this. So Blake, when it comes to correlation, there are three conditions. The conditions are both of your variables are quantitative. The plot shows a linear relationship and there's no extreme outliers. We call this QQ straight enough, no outliers. So you look at this and you say, is it two quantitative variables? Yes, that's why they're getting me over here. Is it two quantitative variables? Yes, it is. Quantitative, quantitative. It's a scatter plot, so it has to be. Scatter plots are made from two quantitative variables. Is there a linear relationship? And that means if you take your data right here and plot a line through it, does the line mostly go through the data? And the answer is yes. Are there extreme outliers? No. Shows exactly, and we call this QQ, straight enough, no outliers. Get ready for Wednesday's class. We'll be chanting it a good bit. QQ means two quantitative variables. So this definitely is good. An extreme outlier would probably be something that's over here because extreme outliers can dictate what a relationship is between two quantitative variables. So if you were to see a point over here, then we'd have a problem with an extreme outlier. We don't usually put ones inside of there because that's a little iffy. And so as soon as we start to go into a far region, we're pointing to an extreme outlier. We have ways to analyze that quantitatively with, I believe, Cook's distance, but we won't do that in 201. We can say that for later classes. So we want to say it's two quantitative variables straight enough and no extreme outliers. The correlation is 0.902. Explain what the researchers have learned about the result of these experiments. Choose the correct answer below. So there is a positive correlation between the placebo improvement and the drug improvement. So it looks like the greater improvement in a study where the placebo shows improvement is also where drug is improvement too. Experiments that showed a greater improvement among patients who took an antidepressant also showed a greater placebo effect. That does sound somewhat accurate. Since it is not appropriate, no. The effect of antidepressants given in an experiment does not appear to be related, no. The experiments that showed, and this is smaller, this is a negative relationship. So they're talking about a positive correlation right here, which is what is indicated here by the value of correlation. And here, the only way this question goes south is if they're saying we can't do it, and it doesn't, because they're making a scatter plot. If you make a scatter plot, you've done, it's two quantitative variables. So really good question right there, Blake. And you can look at the understanding we glean from this is that if you do a scatter plot, that's two quantitative variables. So I felt sure in my answers because it's a scatter plot. Scatter plots are two quantitative variables. We go back to the graphics right here, and you can see scatter plot right here is two quantitative variables. A time plot is a special kind of scatter plot where time is on the x-axis. So a time plot is a special kind of scatter plot. Let's end off with that really, really quick right here. I love making time plots. They're really easy to make, especially with some of the packages we have. So watch this, Blake. You ready? Here's how we make a time plot. We can pull open some of our data, and we'll show a time plot right here to end. Let's go to Aus arrivals. So this is arrivals to Australia on different airlines, or origins to Australia from different countries. And let's go to Aus arrivals, and let's go to autoplot. I think it'll do it. There you go. These are all time plots, layered time plots right there. So that's 4 different time plots. And let's go here and say filter and say origin equals Japan. That's how you spell Japan. And now we can get it just for Japan right there. Oops. Origin equals equals. Yes, I did mean equals equals. Thank you. I forgot logical equals. So there's the origin Japan right there. And we can even go and put this inside of, let's put it to a graphic right here. Graphic 1, let's call it. And let's go ggplotly. I don't have my ggplotly. Library plotly. Random thought, have you seen R's version of funny look? No, what is that? I haven't seen that, Amanda. Maybe I have or I'm forgetting it. Where is that, Amanda? Send it to me. So I bet maybe I have. I don't know. Here we go. Interactive graphic. We'll see what Amanda puts in the tower right there. Have you seen the name? Oh, that we use this funny looking kid. Yes. Yeah, I actually have seen that. When you go to our version, they always do weird R versions. They always call it like weird things. Actually, I have seen that. Yeah. Now it was like, it rings a bell. They've called it like one push-up. They've called it like strawberry shortcake. Fareed, good to see you here. We're finishing off here in just a moment. We saw some time plots right here. A time plot is a special case scatter plot where time is on the x-axis, and we've also drawn a line through the data right here. You're right. It is called Funny Looking Kid. They do such weird names, like names of R versions. You'll see weirdness. Like, let me show you right here. I don't understand. Maybe they have their kids name it. Names of R versions. Where is it? Documenting the version R names. Is this it? Someone's got a tweet right here. All he's saying is make me happy every time I pull it up. That funny looking kid. They've got it somewhere. Why do R versions have funny names? I don't know what they're gonna say. Because our program is funnier with R. Oh my gosh. Would have provided examples for reference, but packages have names that sometimes ggplot grammar graphics dplyr data plus ply for the family of functions related to apply. Oh. Yeah, I don't know. That's interesting. Someone put there was a list of version names. Someone had it here for a while with the different version names. You're welcome, Blake. Yeah, they just do different one push-up was one. There was one called one push-up. Here it is. Or is a GitHub of it? This one might be funny looking kid. One push-up might have been the last one. There it is. So there's one push-up. So I remember one push-up because that was the last one we had right here. Yeah, Fareed, awesome. We love some math here. So they have there's somewhere someone had a webpage with it. So yeah, it was funny looking kid is the latest one. I was like, I had heard that recently. And then one push-up was before that. So yeah, I don't know. And they called it. I remember one push-up. I do not understand why they call it those names because funny R. Well, anyways, that's got it. We'll be back here doing some class here in a little bit. Bye for now, everyone. Bye.